Hello everyone, my name is Saida. I am a data scientist at SI. For today, we're going to cover an important dimensionality reduction technique called Principal Component Analysis or PCA. But first, let's talk about dimensionality reduction and why it is important. Dimensionality reduction is a process of reducing the number of features in a dataset for visualization, compression, and data mining purposes. To illustrate the importance of dimensionality reduction, let's see an example. Consider a dataset of medical records of cancer patients, where each row corresponds to a dataset sample and each column corresponds to a particular feature. In total, there are 35 measurements from 100 patients. When there are a lot of features, it is difficult to see the correlation between them. Therefore, one motivation for dimensionality reduction is data visualization. For example, if we only had one feature in our dataset, which is the radius of the tumor, then it is easy to plot the patients on a number line. And if we have two features, we can plot the data on a two-dimensional graph. If we add another feature, we now have a dataset with three features and can plot the data in 3D. Now let's say we add another fourth feature, the smoothness, and try to represent four-dimensional data in 3D, but with larger dots representing larger smoothness values. However, all these tricks will fail if we want to get a visualization for five-dimensional data. Therefore, reducing dimensions of the data could help to create interpretable visualization. Another motivation for applying dimensionality reduction is data compression. With lots of features, some features containing little to no information could be filtered out. For example, concavity of the tumor is the same across patients and therefore does not add valuable information in cancer identification. One method for dimensionality reduction is Principal Component Analysis or PCA. PCA is a data transformation technique used to reduce the dimensionality of a dataset. For illustration purpose, let's consider a dataset consisting of three features. After applying PCA, we transform three or more dimensional input into a 2D PCA plot. We do so by projecting the data to the new coordinate system in which our features vary the most. Each axis corresponds to principal components, and PCA can tell us how accurately the new coordinates represent the data. Now, let's see the procedure to perform PCA. But before applying PCA, we perform data normalization. Why? Because in PCA, we're interested in the components that maximize the variance. So suppose there are two features, weight and height. If one feature varies less than the another because of their respective scales, kilogram versus meters, PCA might determine that the direction of maximal variance more closely corresponds with the weight axis, if those features are not scaled. Let's see an example of normalizing the radius feature. Specifically, let's derive the normalized value for the first patient. Now, its new value is equal to 0. After applying the same procedure for all values, we get the normalized data. The next step is to calculate the mean value of each feature and then subtract the mean to make the data centered around the origin. In step 3, we want to find the best fitting line to our data that will pass through the origin. The best fitting line will be our first principal component. There are multiple ways to compute principal components, like using covariance matrix or using singular value decomposition. We are going to find the best line, our principal components, using the covariance matrix. For that, we need to calculate this matrix. Covariance measures how two variables, in this case features, vary together. As an example, consider radius and perimeter features. We calculate the mean value for each feature and then compute the covariance using the formula. So the covariance between perimeter and radius is equal to 0.224. It is a positive covariance. It means that when the radius increases, the perimeter also increases. Similarly, when radius decreases, the perimeter also decreases. We are interested in calculating the covariance matrix for our patient dataset. After applying the formula, we get the matrix values. Elements along the main diagonal show the variance within the variable, and the elements outside of the main diagonal show the covariance between a pair of variables. Since the non-diagonal elements in this covariance matrix are positive, we should expect all feature pairs to increase or decrease together. Next step is to calculate the eigenvectors and eigenvalues for the covariance matrix. The eigenvectors will be our principal components. They determine the directions of the new feature space, and the eigenvalues determine their magnitude. To show how they are computed, let's consider the perimeter and radius features. First, we calculate the eigenvalues by solving the following equation, which will give us our eigenvalues. Next, we compute the eigenvectors by solving the system of linear equations for each eigenvalue, and then performing unit normalization to get our final eigenvector. We find the second eigenvector following the same procedure. As mentioned earlier, eigenvectors are our principal components, and the eigenvalues will tell us which is our first principal component and which is our second. We figure it out by sorting the eigenvectors by their eigenvalues in decreasing order. We can see that the second eigenvalue is largest, so the second eigenvector will be in the first column in our resulting matrix of eigenvectors. For now, we saw how to compute the eigenvalues and eigenvectors for only two features, and now let's apply the procedure to our patient records dataset. Since there are three features, we compute three eigenvalues and 3 by 3 matrix of eigenvectors sorted by their eigenvalues. Furthermore, we can measure the variation for each principal component. We want to know to how much variation in the data each principal component contributes. For that, we'll calculate the variations for all principal components and then calculate the total variation. As we can see, principal component 1 accounts to 92.5% of the total variation among the principal components, and principal component 2 accounts to 7.5%. Finally, principal component 3 accounts to only 0.01% of the total variations. Since principal components 1 and 2 contribute nearly to 100% of the variations, we can discard principal component 3. Now, when we computed the principal components, we need to transform our dataset to new coordinates. For that, we perform matrix multiplication between transposed matrix of eigenvectors, where each row represents an eigenvector, with the most significant eigenvector being at top, and the original data, with each row holding a separate dimension. In the final data, each column represents a data instance in the new coordinates. Finally, let's plot the data points in the new coordinates. As a result, by using PCA, we transform 3D data into 2D space. We can also see that the first principal component contributes to the most variations in the data.